Hello everyone. Today we are going to present our NLP final project. The topic is the LMSYS Chatbot Arena Human Preference Predictions. Our team members are listed here on this slide. Okay, let's jump right in. Here's the outline for today's presentation. First, we will give an overview of the competition and the data so you will understand the background. Next, we will analyze two top solutions, specifically the 4th place and the 13th place on Kaggle, to see what techniques work for them. Finally, we will share our own insights, our future plan, and show you our current progress with the experiment. So, let's look at the goal of this competition. Basically, we need to build an automated AI judge that mimics how humans evaluate text. The system gives us a user prompt and 2 responses generated by anonymous chatbot. Our job is to analyze them and predict the human preference. Does model A win? Or does model B win? Or is it a tie? A key feature here is the scoring metric, which is log loss. This means we cannot just guess the winner. Our model has to output a probability distribution for the 3 outcomes. This metric heavily penalizes bad calibration. In other words, if our model is confident but wrong, we lose a lot of points. For the data, we have about 55,000 samples for training and 25,000 for testing. The input is simple, just the prompt and the 2 responses. The tricky part is in the metadata. In the training set, we can see the model names like GPT-4 or Claude. But in the test set, these identities are hidden. So we cannot rely on brand names to judge quality. We cannot just assume GPT-4 is better. We have to analyze the actual content of the text. That's the real challenge. Now, let's look at the 4th place solution on Kaggle. They use Gemma 2 9B with LoRa fine-tuning. Instead of using it as a standard text generator, they changed the final output layer to a 3-class classifier, so they predict A, B, or tie directly. This solution gave us some good hint on avoiding errors. For example, the test data might have empty strings or failed responses. We need to handle these edge cases so the code doesn't crash. Their trick was simple. If a response is null or an error, they just hardcode a vote for another model. This ensures robustness during submission. They also tackle positional bias. LLMs often prefer the first response they see. To fix this, they use test time augmentation, TTA. Basically, they run inference twice, once normally and the other one with the responses swapped, then average the probabilities. Next, look at this chart. This is their smart truncation strategy. When the conversation is too long, they have to cut text. They use proportional truncation This ensures we keep the prompt and both responses balanced. We won't end up with just a prompt or a half-cut response. They also filter out low-quality data. If less than 80 tokens remain after cutting, they just discard that round entirely. They found these thresholds by analyzing the training set. Moving on to the 13-place solution on Kaggle. The author used a more complex 3-stage transfer learning pipeline. First, they did task adaptation using general dataset like ultra feedback, then domain adaptation, and finally fine-tune on the competition data. For the architecture, they found the 7B to 9B size range worked best, specifically assembling Llama 3.1 and Gemma 2. A key technical detail is the loss function. They combine cross-entropy with focal loss to help the model focus on hard samples. They also apply multi-sample dropout in the decoder, which is a bit unusual, but worked well. On the engineering side, they improved the input structure using turn alteration. Instead of putting all of Model A's text first, then Model B's, they interleaved them. Model A speaks, then Model B speaks. This is more natural for a conversation. They also use left truncation, meaning they cut from the beginning to keep the newest information. During inference, they added a refusal penalty. If a model says, as an AI, I cannot, they automatically give point to the opponent. Finally, to optimize log loss, they renormalized the output probability to align with the ground truth distribution in the training data. So, based on this insight, here is our plan for improvement. We have 5 main points. First, sandwich tokenization. We will keep the first 20% of the prompt and the last 40% of the responses. This ensures the model sees the instruction and the conclusion without exceeding the context limit. Number 2, efficiency. We will stick with LoRa fine-tuning and 4-bit quantization. 3, data augmentation. We will swap response pairs during training to remove positional bias. Number 4, testing. We will use TTA and try the newer Gemma 3 architecture to compare with our baseline. Number 5, architecture. Following the second place strategy, we plan to replace the output layer with a custom NLP head to capture more complex logic. For our experiment, we are using lab resources, 1 RTX 4090 and 1 A100 GPUs. First, we'll fine-tune a deburter model just to verify if our sandwich tokenization strategy works. Then we move to Gemma. We tried Gemma 2 9B, which was popular last year. Since Gemma 3 just came out, we also tested the small 1B version to see if it could match the performance with fewer parameters. We also double our data by swapping response A and B to fight bias. However, we found 1B model wasn't accurate enough, so we decided to move up to the 4B and 12B versions and will apply TTA during inference. Here are our current scores. For the beta with sandwich tokenization, our public score improved slightly over the baseline, but the private score actually dropped. The results were a bit mixed. For Gemma 2, 9B, the fine-tuning didn't meet our expectations. We suspect our LoRa rank of 16 was too low for this task. We plan to increase the rank and try again. Finally, the result for Gemma 3 1B. We tested sandwich tokenization combined with swapping responses. The data augmentation definitely helped improve the score. But honestly, compared to the beta or Gemma 2, the overall performance is still lagging behind. Our conclusion is that the 1B model is just too small for this specific task. Moving forward, we will focus our experiment on the larger versions of Gemma 3. Thank you for listening. Have a good day.